Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks, section 12.2, titled Unions and Complements of Events. Alright, so if you recall from section 12.1, an event is just a set, right? It is a set of outcomes of an experiment or it's a subset of the sample space, right? The list of all possible outcomes. So when they talk about unions of events, that's a union of two sets. And the complement of an event is the complement of that set. And you've seen unions and complements before. So you're calculating probabilities for unions of events. We'll start with unions. Now hopefully you remember the inclusion-exclusion principle. In fact, let me write that down for two sets at least. I think we're only going into two sets in some of these examples. But this is back in chapter 10 on counting. Right, the inclusion-exclusion principle. For two sets, remember the cardinality of A union B, right? So the number of elements that are in A or in B or both was the number of elements in set A plus the number of elements in set B minus the number of elements in their intersection, right? The number of elements that were in both A and B. And this extended to 3 elements and 4 elements and whatnot. And if you want to go back and into chapter 10, I forget exactly what section, and look at that section on the inclusion-exclusion principle. If you remember this, you'll have no problem finding the probability of the union of two events. Because all you need to do is count. We're going to be looking at those scenarios where we have the uniform distribution, right, where every outcome in the sample space has the same probability. Every outcome is equally likely. And in those cases, when you're calculating probability of an event, you just count the number of elements in that event and divide it by the number of elements in the sample space. And if the event is a union of two other events, well, you can count the number of elements in that union using the inclusion-exclusion principle. And the first part of this goes over, well, what if the intersection is empty? Right? What if they're non-overlapping? So that means that they're disjoint or mutually exclusive. Well, then this becomes even easier. Right? Recall that two events are mutually exclusive if the two events are disjoint. Right, the intersection is empty. So it follows from the definition of probability of an event that if E1, right, say event E1, and another event called E2, if these two are mutually exclusive, they have no outcomes in common, then their probability, the probability of the union of E1 and E2, will just be the sum of their individual probabilities. Again, that would simply be because the cardinality of E1 and E2, union E2 would be the cardinality of E1 plus the cardinality of E2, and then all that would be divided by the cardinality of the sample space. So you get the sum of the probabilities equals the probability of the union. Alright, so their example they're talking about here, they say, suppose we would like to calculate the probability that a 5-card hand, right, from a deck of 52 cards, has at least 4 face cards, right? And the face cards, have faces on them: the jack, the queen, the king. It is easier to determine the probability that the 5-card hand has exactly 4 face cards or exactly 5 face cards, and then adding them, right? Because you can't have both. You can't have exactly 4 face cards in your hand and exactly 5 face cards in your hand at the same time. So they're calling this event F4 the event of having 4 face cards in your hand, exactly. And they're calling F5 the event that you have, exactly 5 face cards in your hand. and their intersection would be empty, right? Because again, you can't have both. Can't have exactly 4 and exactly 5 face cards at the same time. Then you see it's just counting, more counting. You saw this in section 12.1, all these probabilities that we're calculating, under the uniform distribution where all outcomes are equally likely. You're just applying your counting principles from chapters 10 and 11. So like for F4, having exactly 4 face cards. Well, there are 12 face cards, right? There's the Jack of hearts, diamonds, clubs, and spades, right? And then so there's 4 jacks, 4 queens, 4 kings. There's 12 face cards. You just choose 4 of them. 12 choose 4, and then applying that fundamental principle of counting, the multiplication principle, I multiply that by my choice for the other card, right? Because I got 4 face cards now. And now this other card can't be a face card. And if there are 12 face cards, right, that means there are 40 non-face cards. So you see I have 12 choose 4 for my choice of the 4 face cards times my choice of some other card, non-face card, the 40 there. And then F5, where all 5 of them are face cards. The number of ways that could happen is 12 choose 5, right? You take the 12 face cards and choose 5 of them to be in your hand. So the probability of having either this or this, of having at least 4 face cards in your hand, is 12 choose 4 times 40 out of 52 choose 5. Remember, 52 choose 5 was the total number of outcomes, the size of the sample space. Right? 52 card deck, choose 5 of them. Plus, then the probability of F5, 12 choose 5 divided by 52 choose 5. Right? And again, I'm not saying it's as simple as that, but it really is. And you have to just remember how to count. Right? All your counting principles from chapters 10 and 11. All right, so the first activity is just, are the events mutually exclusive? Are they disjoint? Do they share any outcomes? Can they happen at the same time? Because again, mutually exclusive events can't happen at the same time. Their intersection is empty. So how about if I tossed a coin 5 times? Event A is the first 3 flips come up heads. And event B is the last 3 flips come up tails. Can these happen at the same time? No. Because if the first 3 flips come up heads, if A happens, only the last 2 could be tails, not the last 3. Because there's only 5 flips. So these can't happen at the same time. They are mutually exclusive. How about a coin is tossed 6 times in those events? Now these can happen at the same time. Right? The first 3 can be heads, and then the second 3, because there are 6 flips, can be tails. So these events are, under this experiment, are not mutually exclusive because they can occur at the same time. How about a 5-card hand is dealt from a standard playing deck of 52 cards? Event A is the hand has 3 aces. Event B is the hand has a pair of kings. Well, yes, you can have 3 aces and 2 kings in your 5-card hand, so these are not mutually exclusive because they can happen at the same time. But can you have, if you only have a 5-card hand, you can't have 3 aces and 3 kings. That's 6 cards, so these are mutually exclusive. So I hope that makes sense, what the term mutually exclusive means. Disjoint, can't happen at the same time. Their intersection is empty. They share no outcomes, however you want to put it. All right. Now, if 2 events are not mutually exclusive, The probability of the union of events can be determined by a version of the, and as I mentioned this before, the inclusion-exclusion principle. The probability of E1 union E2 is the probability of E1 plus the probability of E2 minus the probability of their intersection, the probability that both events happen at the same time. And again, it's all about counting. You're just going to count the number of elements in E1 union E2 using the inclusion-exclusion principle, and then divide that by the total size of the sample space. And they give this a draw, and you can watch this animation here explaining this. This is the same really as the animation when they talked about the inclusion-exclusion principle for two sets. All right. So you can again read. This is there was an example on this in section 12.1. So if you haven't read that redundant data storage example in 12.1, please go back and read that, and then read this, because I'm going to leave this to you. All right, so let's do an activity on our own where we have to do this ourselves. All right, so the following questions pertain to an experiment in which a fair coin is flipped 3 times. So we're asked to define the following 3 events. A is the first 2 flips come up heads. B is the last 2 flips come up heads. And C is the last 2 flips come up tails. So enter your answer as a simplified fraction. Okay. I mean, unless they ask you a yes or no question. Are events A and C mutually exclusive? So again, there's only 3 coin flips here. If the first 2 are heads, the last 2 can't be tails. So A and C, there's only one slot left, one flip left. So if the first 2 are heads, the last 1 can be a tail, but not the last 2. So A and C are mutually exclusive, right? So I'll put yes, right? They can't happen at the same time. What is the probability that the first 2 flips come up heads and the last 2 flips come up tails? Well, I just told you that those cannot happen at the same time. So if those can't, so A intersects C is empty, right? There's no outcome in A intersects C. So the probability of this happening is 0. All right. If an event is impossible, its probability is 0. So then what would be the probability of A union C? Well, since A and C are mutually exclusive, the probability of A, and I'll write this out now. Right? So the probability of, A union C, since A and C are mutually exclusive, is going to be the probability of A plus the probability of C. Now, what's the cardinality of A? Well, A was the first 2 flips are heads. So again, imagine I got 3 slots, 3 flips. These have to be heads. So I have one choice for both of those. And then the last one can be anything. I got 2 choices for that. So the cardinality A is 2. There are 2 outcomes here. There's heads, 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 tails. And what's the cardinality of C? Well, that would also be 2, right? Because again, you got 3 coin flips, and event C is the last 2 flips have to be tails. So you have 1 choice for each of those and 2 for the first one. So 2 out, heads, tails, 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 tails. And then what's the size of the sample space? Remember, S was the sample space, the list of all possible outcomes. And if you're flipping a coin 3 times, you have 2 possibilities each. 2 times 2 times 2 is 8. And you saw this in section 12.1 as well. So these probabilities are 2 out of 8, plus 2 out of 8, which is 4 out of 8, or reduced to 1/2. So the probability that, if you flip a coin 3 times, a fair coin, the probability that the first 2 are heads or the last 2 are heads or tails is a half. You have a 50% chance of either one of that event happening. So this probability is 1/2. Okay. All right, now are the events A and B mutually exclusive? Can the first 2 flips be heads and the last 2 flips be heads? Well, yeah, if all 3 flips were heads, the first 2 would be heads and the last 2 would be heads. So these can happen at the same time. So these are not mutually exclusive. All right. Then what is the probability that they both happen at the same time? Well, again, there's 8 outcomes total. And well, if they all have to be heads, right? If both of these happen, if the first 2 flips are heads and the last 2 flips are heads, that's just the outcome heads, heads, heads. So there's one outcome in the intersection. So the probability of both of those occurring is 1 out of 8. All right, and then what would be the probability of their union? Now again, this would be the probability of A, and I'll write this out for you. The probability of A union B, where these events are not mutually exclusive, would be the probability of A plus the probability of B, then minus the probability of their intersection, A and B, A intersect B. And, again, this would be 2 out of 8. This would also be, for the same reason that, if the last 2 are heads is the same as if the last 2 are tails. So this would also be 2 out of 8 like before. But then minus 1 out of 8, right? And the reason we're subtracting that 1 is because, you really counted the heads, heads, heads twice. You don't want to count things twice, so you take one of those away. And this is 3 out of 8. So you have a 37.5% chance of this happening, of having heads on the first 2 flips or heads on the second 2 flips, or both. So 3 out of 8. All right, so now that we got that out, again, the union, just remember your inclusion, exclusion principle. That'll really help. And again, all the counting principles, how to count. We've seen this before too, how to count the number of objects, the size of the complement of an event, right? Not how many elements are not in a set. Well, you just take all the elements and subtract the elements that are in the set. Take all the elements in the sample, all the outcomes in the sample space, and take away all the elements in so in E. If I want to count the number of elements in not E, so you just have to remember this. Right, you have to remember how to count by complement. All right, pardon me. You just have to remember this. Remember, S is the sample space. Sorry if you can hear my dog. I apologize. And E is some event. So remember, like a little Venn diagram. Say this. Remember, S is the all possible outcomes. E is some subset of that. Say this circle represents all the outcomes in E. Well, then, not E, right? The complement E bar would be everything outside that circle. So if you want all the elements in E bar, just take all the elements in S and subtract the elements from E. All right, if you want to know how many elements are in E bar, you take everything and then take away E, and then you've got E bar. Right. And then when it comes to the probabilities then, right, if I divide everything by the cardinality of S, Then we have this here is going to be the probability of not E equals, and then dividing each of these by the cardinality of S, we get 1 minus, and then the probability of E. Right? Because remember, when we have this, the uniform distribution, when every outcome is equally likely, probability is just, of an event is just the size of that event divided by the size of the sample space. And that's where this formula is coming from, right? They're telling us right here. All right, so they have an example there for you, and I'll just get right to the activity. They don't even have a challenge activity here. How weak is that? All right, so a participation activity here. Enter your answers as simplified fractions. So number 1. So that's another one of those coin is flipped 3 times. A fair coin is flipped 3 times. What is the probability that there is at least one head? All right, so I'll go to some paper here. So if this event is, at least one head, flipping at least one head, let's say 1H. What's the opposite of that? Well, the opposite of one or more heads, that's at least one, is no heads. No H's. Or, in other words, all 3 are tails, right? Flip. This is just the set with the outcome tails, tails, tails. So the probability of this is 1/8. Remember that when you flip 3 coins, or flip a fair coin 3 times, there were 8 possible outcomes. So the probability of E is 1 minus the probability of E bar. All right, again, you can just switch these and you get the other formula, same thing. So the probability of flipping at least one head is 1 minus 1/8 is 7/8. And I know there aren't that many outcomes here. You could have just counted them. All right, you could have just listed all 8 of them and say, hey, 7 of these have one head or more. And say 7 out of 8. But they're asking us to try to implement this rule, this complement rule. So you have a 7 in 8 chance, right, of flipping at least one head. Right, here, if a fair coin is flipped 10 times, what is the probability that there is at least one head? So again, I wouldn't want to list these out because again, if there are 10 flips, there's 1,024 outcomes. I'm not going to write those down. The opposite of at least one head is no heads. Well, what if all of them were tails? Well, that's one outcome out of the 1,024. And then I subtract that from 1, and I'll get the probability of flipping at least one head. So 1 minus 1 over 1,024 would be 1,023 out of 1,024. Right? The probability of flipping at least one head. Finally here, if a roll of a blue and a red die, what is the probability that the sum of the numbers is at most 10? All right, so you may recall from maybe section 12.1, you flip two die. Now these are 6-sided die. Okay. If I flip a blue and a red die, blue die, red die. Remember there were 36, the cardinality of the sample space was 36, right? Because there's 6 possibilities here times 6 possibilities here. Right? And they listed them as ordered pairs back in section 12.1. Now the event is the sum of the numbers on these dice is at most 10. Now at most 10 means, less than or equal to 10. 10 or less. Right? So what I have to do here, you know, you could find out, how many have a sum of 2, how many outcomes will the numbers add up to 2, to 3, to 4, to 5, to 6, to 7, to 8, to 9, to 10, and count all those up, and then divide by 36. But that's a lot. That's a lot. I'd rather look at the opposite of this. Now, the opposite of at most 10, being less than or equal to 10, is being greater than 10, right? The sum is greater than 10, which in terms of dice, if these are two 6-sided die, this means 11 or 12, right? Because the highest it can get is 6 plus 6. And being greater than 10, that's 11 or 12. So this event has these outcomes. Now again, I'll do the ordered pairs like this, where you have the outcome of the blue die, then the outcome of the red die. So the ones that get a sum of 11 are 5 then 6, 5 on the red, blue, 6 on the red, or 6 then 5, right? Those add up to 11, and 6 and 6, and that's it. Those are the only 3 outcomes out of all 36 of them that have a sum greater than, the sum of the numbers is greater than 10. So the probability of, not E is 3 out of 36, which is 1/12. So that means the probability of E, right, the probability of, the numbers adding up to at most 10 is, 1 minus this, which would be 11/12. Right, and if 3 outcomes are in here, that means the other 33 outcomes are over here. There would be 33 out of 36, or 11 out of 12. All right, 11 out of 12. Okay. And pretty simple, I feel. Use some counting principles and whatnot, and you'll have to use more counting principles and probably in some of these exercises when you're trying to count how many elements, how many outcomes are in certain events and certain sets. Again, if you're unfamiliar with Chapter 10, Chapter 11 material, I highly suggest you go back and review some of that stuff, those counting principles. Alright, so you got your additional exercises. Again, some of these are on your latest assignments, some are not. I would still recommend looking at all of them just to practice, get extra practice, get extra exposure to the material. You can also look at the solutions if you need to, just to check yourself, right? Please try to work on them first, right? Try to figure out the answers first, and then look at the solutions to see how you did. You're not going to learn anything if you're just looking at the solutions straight away and copying them without working, without trying. And I'm hoping my video here is a good guide for this section. If you have any questions, of course, send me a message and I'll get back to you as soon as I possibly can. And thank you very much for watching.